Hey guys, welcome. Yeah, so I have a really interesting limit question for you, and it's a lesson on when not to l'hôpital. I will say more, but first, may the Lord Jesus Christ bless this day, bless this video, you and I, and may He give us the strength to continue to fight the good fight. Alright, now, what did I mean? Well, you should not shoot a fly with a shotgun, or so they say, and that's a good saying in this case, which is basically saying, like, choose your weapons, right? Like, yeah. So here it goes. This is the limit we're looking at. It is lim it's x goes to 0 of 1 minus, and its cosine x to the 5th, that 5 don't like it, over I already had a really good recording of this video. I'm re-recording it because basically, like, I didn't feel my horizontal lines were horizontal enough, and just a few kinks basically. Otherwise, I had already recorded this solution, and I was pretty satisfied with what I did. Anyway, let's be careful to draw our horizontal lines so I don't have to do this again. That's yeah, the point of what I said. Okay, so if we, as usual, just plug in 0 to start, what we're gonna get, and that's what you need to do first, just plug it in to see what what happens. And what happens is you're gonna get 1 minus 1, because cosine of 0 is 1, remember? And then the denominator is obviously 2 times 0 to the 10th, that's 0. So this is 0 over 0. And so then one would think we can use L'Hôpital's rule, and in fact we can use L'Hôpital's rule. But I said at the start, this is a lesson on when not to L'Hôpital, right? So I'm saying L'Hôpital's rule is probably a bad idea, but let's try L'Hôpital's rule and find out why it's a bad idea. Okay, first, what L'Hôpital's rule said, if you need a quick reminder, is limit is x goes to a of f of x over g of x is equal to 0 over 0 or infinity over infinity. Then do lim is x goes to a of f prime of x over g prime of x, and check that out, and hopefully it works out for you. And if it doesn't, what you do is you do it for double primes, and hopefully it works out then. If it doesn't, you keep doing it, right? That's what L'Hôpital's rule said. If you have 0 over 0 or infinity over infinity, right? Okay, and notice that this is not the quotient rule. When I had single derivatives, or when I had the double derivatives on both f and g, that's not the quotient rule. Let's just take the derivative of the numerator by itself, divide by the derivative of the denominator by itself, right? Okay. And so I was saying, like, somewhere along the line it will work out. All right. So that's hopeful, and so let's do that. So we go lim as x goes to 0, and then we go derivative of the numerator, well, derivative of 1 is 0, and then you've got minus derivative of cosine is negative sine, so you've got negative sine of x to the 5th, and then by chain rule times 5x to the 4th, right? Okay, cool. Now minus back to back, they like cancel, so to speak, right? Well, they turn into plus. And so we could do that. So we're done with taking the derivative of the numerator, and then we do divide by the derivative of the denominator. Derivative of the denominator is what is it, 20x to the 9th, right? So we evaluate this limit. Clearly, when we evaluate it, we get 0 over 0. Okay, so L'Hôpital said, I mean, actually it's Euler's rule. Like, L'Hôpital was like just a rich Frenchman who like took credit for it, probably paid Euler or something, but it's actually Euler who came up with it. So from here on out, I'm going to call it Euler's rule. I already said this in a previous video, this little background story, but I'll say it again until everyone is informed of this mathematical conspiracy. Okay, so 0 over 0. Alright, so what? So we do it again. Take the derivative of the numerator, divide by the derivative of the denominator, and then again evaluate the limit as x goes to 0. But wait. Like, I want to think about this. Like, this does not look like the path we should be on. And why? Because, well, notice that in the numerator we have a product between, let's say, f of x is sine x to the 5th, and then g of x, which is 5x to the 4th. So when we take the derivative of the numerator by itself, we're going to need the product rule. Specifically, we have to write f prime g plus fg prime. For 1, that's a lot, right? Like, it's going to get messier. Okay, I don't like that. For 2, notice that f prime g will have some x term in it, x to a power, and so will fg prime. Without even doing it, you should understand that. Since g is this, g prime is going to be what? Like 20x to the third. So this will have a 20x to the third. And then this will have at least, it will have more because from the f maybe like, anyway, like this will have at least 20x to the third, and this will have g, so we'll have x to the fourth. So both of these will have x to a power. So when we plug in 0, we'll have 0 plus 0, which is 0, and then the denominator will have derivative. What is it going to be? It's going to be like a lot, right? 180x to the 8th, and this is clearly also going to be 0. So in the next step, we're going to get 0 over 0. So we're going to have to keep doing it, but that means then we do product rule and product rule like on this part for the next step. Okay, that's getting even messier. This can't be the path. Now notice that the denominator will eventually work out. At least that I could be satisfied with. How exactly? Well, after 8 more derivatives, I know the denominator will turn into a constant, and the constant will be like 180 times, it will be 180 times 8 factorial, or if you like think back at what we did, this is going to be the same as 2 times 10 factorial, right? Anyway, the point is that after so many derivatives, the denominator will turn into a constant, and that's kind of the gimmick that like leads one to know that like L'Hopital's rule is a good idea usually, right? Especially when you have a single polynomial term, because you know eventually it will turn into a constant. Nice. But as I said, the numerator keeps getting uglier, and plus, like, it's going to take so many steps to get to this, and we're not going to do this. Like, this is a mess. So what do? Well. We do this. And that is, we're going to multiply this quotient by the only thing we're allowed to multiply by, which is uno. Now, that means that we should choose whatever we want to be the 1 over here carefully. So that's this. And obviously if I multiply the numerator by this, I have to multiply the denominator by it also, so that way, as I said, we multiply by uno. Okay? Alright, so why did I know to multiply by that? Because clearly now the numerator is of the form a minus b times a plus b, which is a squared minus b squared using difference of squares. So it is 1 minus cosine squared x to the 5th. Now we know from trigonometry that 1 minus cosine of stuff, right? 1 minus cosine of stuff, 1 minus cosine squared of stuff, sorry guys, 1 minus cosine squared of stuff is equal to sine squared of stuff. And that's the insight that told us we should multiply the numerator by this. We knew it'd create a difference of squares, and it'd get us to this, where clearly stuff is x to the 5th, so we know that this is equal to sine squared of stuff, namely sine squared of x to the 5th. So this is sine squared of x to the 5th. Nice. And we know that that's got to somehow be helpful. Well, because the other path we took like wasn't helpful. So now we go, alright, so this is the same as limit as x goes to 0 of, again, that turns into first this and then second that, right? And third, let's erase that a little bit. Okay, so sine squared of x to the 5th. Over what? Well, our denominator has gotten bigger, but that's okay. Like, we'll live with it. So it's going to be 2x to the 10th, and then times 1 plus cosine of x to the 5th. Got it. Okay. Now, this is what I'm going to write. I'm going to write that what I've got is the same as, this is the same as lim as x goes to 0 of 1 over, I'll lead with this, 1 plus cosine x to the 5th. I could have put it at the end, but I could do it in front if I want. So that's like, I just threw a 1 here and wrote 1 over this, which is that. And so now I'm going to write times sine x to the 5th I want a little bit of space, sorry guys, you'll see why. Sine x to the 5th over x to the 5th. Okay, so then I have to now, at the tail end here, write sine x to the 5th over 2x to the 5th, right? Cool, right? Like, because sine x to the 5th times sine x to the 5th retains the sine squared x to the 5th in the numerator, good. X to the 5th times 2x to the 5th retains the 2x to the 10th, and obviously this is that, right? Okay, now we can use a limit law that says the limit of the products is equal to the products of the limits. So the products being this, this, and this, so the limit of the products is the same as the product of the limits. So I'm saying I could write limits x goes to 0 here, and notice that this is really a 1/2, and so 1/2, but from the limit law, I could write limits x goes to 0 here. Okay, another limit law tells me that I could put the constant in front of the limit. So I could write, in this part, I could write 1/2 lim is x goes to 0, right? Okay, cool. So there we are. Now, here, we have no issue plugging in 0, because cosine of 0 is 1. So I get 1 over 1 plus 1, and so 1/2. So I see that this limit here is 1/2. Nice. And so we have times this limit. Deja vu, no? Okay, have you seen that before? I have a video on it, but remember that famous limit that we use the squeeze theorem to prove? That says limits theta goes to 0 of sine theta over theta is equal to 1. Well, here, if you let theta equal x to the 5th, right? Then we have sine theta over theta being sine x to the 5th over x to the 5th. Now, the only question is theta goes to 0, does x go to 0? Yeah, because as theta goes to 0, x to the 5th goes to 0, but as x to the 5th goes to 0, x goes to 0, and vice versa, right? As x goes to 0, x to the 5th goes to 0. In other words, don't worry that I have a theta here, and so I have an x over here, but theta is x to the 5th. In this part, we're good, right? In short, when you're doing this limit, right, the only thing you're worried about is, well, the variable here agrees with whatever variable is used here, but more importantly, whatever is in here is the same as whatever is in the denominator. That's the only thing you're concerned about. You're not concerned about a constant missing in this part as long as it involves the same variable as over there, right? Okay. So in short, that's all to say that this limit here is equal to 1, right? Okay. And clearly this limit is the same as this limit, and so this must be a 1, but there's a 1/2 in front of it. So this whole thing at the end, this guy in the square brackets is 1/2 because it's 1/2 times 1. Alright, so grand total 1/2 times 1 times 1/2 says our answer is a quarter. Right? It's a quarter. And I'm done.